For those of you who don't know, one of you, I am part of the Flex cohort. Today I'm going to be talking about artificial intelligence. When I kind of started looking into this all of 2 days ago, I decided, I'm going to roll something out, and it turned into kind of a monster. What I did end up doing was creating a Connect 4 fully functional web-based AI. It's pretty, it's not buggy in that it doesn't work, but I think there's some weird stuff going on towards the end of games, but it actually plays pretty well. I encourage you guys all to try it out at some point. But anyway, artificial intelligence. I think we all have a pretty good handle on what it is, but the field itself really came to the forefront of computer science like in the 50s, pretty much. Really hasn't left since then. There's been a lot of amazing breakthroughs along the way, especially lately. Obviously, it's a pretty big area to talk about. So I'm going to really drill down specifically into games and particular types of games and what algorithms are used to help attack those games for machines. So the definition of artificial intelligence is not all that great. The word intelligence is kind of in it. It's kind of a cyclical definition, right? So it's kind of something that we intuitively grasp what intelligence is, but it's kind of hard to put into words succinctly. So you'd have to kind of be crazy to ask that question out loud, but why not? So what is intelligence? It's broken down into a bunch of different things. I tried to group it together. All of these are very important. Communication and learning are really right now the cutting edge of where everything seems to be going. I'm going to focus on the underlined bullet point there: abstract thought, problem solving, and planning, all of which really, in my opinion, really tie into games, and particularly board games that require strategy and trying to outthink your opponent. And on a personal note, I love board games. I am a huge chess nerd, so that's pretty much the draw for me. But I think also games really do kind of reflect who we are as people. It's kind of like what we aspire to be. It very much reflects, I think, humanity's achievements and kind of creates a fair and controlled playing field and environment to compete in. So it kind of lends itself well to computers in that way. So just a quick history and a graph, just to give an idea of some of the complexity, and then I'll come back to this real quick. So you have tic-tac-toe here. Now this is essentially a logarithmic graph, so this isn't drawn to linear scale by any means. So tic-tac-toe has 9 squares, as we all know, 3 possibilities for each square. That represents about 20 to 30,000 unique positions. Connect 4 is the next one on the list, the one that I wrote the code for. It's 10 billion times as many positions as the previous one. Backgammon and checkers are both 10 million times as much as Connect 4, and so on and so on. Recently, of note, I don't know if you guys know this, Go, which is, I think, really big in Asia, is extremely complex, obviously. Computer scientists in the field pretty much had predicted that it would be another 10 years or so, even with a lot of the breakthroughs that were coming through with neural networks, that it would take that long to be at the championship level. But Google developed an algorithm, a neural network that won 4 out of 5 against one of the world's leading players as recently as a couple months ago, which is pretty cool. Anyway, so chess, all these other games, some have been solved. Connect 4 has been solved. It's actually a win for player 1 if played perfectly, which is kind of interesting. And anyway, so we might come back to this later if I have time. So I'm going to talk about something called the Minimax Algorithm. Now this would apply to many of these games, actually, most famously chess. The algorithm itself is probably easier shown than explained, but it's a recursive algorithm. It's a depth-first tree, actually, that usually is used for N or 2-player games. It's made for games where you know all the information. It's not really great for poker, for example. So there's a recursive tree-based search, and the funny thing is the Minimax algorithm itself doesn't care about the game it's playing. All it knows is numbers. So it assigns a value to different positions, and its goal is to maximize that number. So there's a secondary function called an evaluation function that's used to kind of translate the particulars of a game into what the approximate value of that position is. So without getting too crazy, let's go through a pretty simple example. This is called tic-tac-toe. Does anyone not know how to play? If so, just please leave. So this is a pretty ridiculous position that would probably never occur in a real game. I personally I'm a big fan of the middle square. So it's X's turn, right? Because we're not heathens. We don't let O go first. So anyone know what the solution is for For this specific, okay. So basically, the Minimax algorithm doesn't really care. It's an exhaustive search. So X has 3 squares that it can go to. So this is essentially a visual of how this algorithm works. So the first one, let's make it the easy one, the middle square. It then evaluates, the evaluation function evaluates the position and says, okay, hey, I won. So that's plus 100. In reality, you'd probably make it plus whatever the max integer value is. A really big number, right? Because that's your goal in the game, to win. So that branch of the tree is done because it reached the end of the game. The next one, let's say X goes on top. So this is not complete, obviously. The game is not won. So now this is where things, I think, get a little interesting, or at least less boring. So now it's from O's perspective, right? So X made his move, and now within the tree, it's O's turn. So this is where the mini part comes from the Minimax algorithm. Everything gets flipped on its side. From O's perspective, he wants to give X the hardest time possible. So he has 2 choices to make, right? Because X already took the top square. So the first one is in the middle. And again, the order is not important here. It's going to do all of them. It sees that it wins now. So that's a negative 100, which is, again, from X's perspective, because it's X's turn. It could also go to the side, in which case the game is still not complete. So we go yet again to the next level. So it's basically we're creating a tree, similar to the trees we looked at earlier in the cohort. So finally, there's 1 square left. X goes. It wins, plus 100. So this branch is done. So the value propagates. Damn it, I hit the wrong thing. Okay, so just to review, okay, so the 100 propagates back up. So now, again, all of O's, well, only 2 possibilities, but all were exhausted and calculated. So now it has a simple choice to pick the minimum of the 2, because again, it wants to screw X over, so to speak. So the negative 100 is chosen, and now that's propagated back up to the X level. But X still has 1 more move to try. And this is very similar to the middle one where O can either win or let X win, essentially. Same idea. So the plus 100 propagates up. O picks the negative 100 because it wants to. And now X can finally choose the question?
Yeah. So this is making the assumption that O is going to
want to beat you?
Yeah.
Yeah. So that's the underlying assumption of this is, I mean, even as people, when we play a game, we assume our opponents are going to play the best moves.
Right.
Yeah, I mean, there might be some gotchas in certain cases, but for the most part, it's a perfect game. There's perfect information, so you can make that assumption and you'll still win if it's if they play suboptimally or at least do as well. So finally, X picks the plus 100 and makes the move, and all is right with the world. So again, just real quick to go back to this chart. So tic-tac-toe is, again, Connect 4 is 10 billion times as complicated. I was going to roll a Go thing, but I didn't want to overwhelm you guys, so I figured I'd just settle on the Connect 4 one. But you can see the problem here is that even in tic-tac-toe, even though you only have 9 squares and three possibilities for each square, the possibilities go up to 30,000. So the branching gets kind of ridiculous. So this tree that we made, imagine being just millions and millions of nodes. So you can't always go to exhaustion. You can't go to the end of the game. It's just not feasible. So what you have to do is a variation of the Minimax algorithm, and I'm not going to go into the same level of detail, is that you would kind of pick a depth that all your nodes would go to. And when it reaches that depth, you essentially have to have that evaluation function. Okay, it's not going to be plus or minus infinity. It's going to be some number that is well structured. So when it comes to Connect 4, when I wrote the code, I had to take into account, okay, 3 in a row is really good, right? Because you're threatening 4 in a row. 2 in a row is better than 1 in a row. So you kind of have to play with the values a little bit and let it play and see how it goes. Okay, so.
You got to pick a leg,
John. Sweet. So that is, unfortunately, I don't have too much. Well, actually, it kind of works out, I guess. Okay, so that is pretty much it, actually. I encourage you guys all to check out the game. Okay, I didn't, okay, so it's, again, I really went nuts with the GUI here. It's really fancy.
Can you send the URL to the Slack channel?
I will absolutely send it. I was also going to put my code on Git at some point once it's worthy of being seen. But I mean, I kind of hacked it together pretty quickly. But essentially, so this is all running on the browser. It's all running through JavaScript. And it's not a pushover. The tree depth I had to set for this is 6 ply, so it's able to look 3 complete moves, my move, his move, ahead. I've played it a few times. It's actually not bad. I mean, I've beaten it a few times. It's beaten me a few times. Let's see if it's smart. Yep, see, it blocked me. So it's, again, it was fun. It was fun to make. It took longer than I thought it would. And who knows, maybe for my stackathon, I'll build on it for something more interesting. So, thank you, guys.